talk about my works in the past 3 years during my ConFlex fellowship. And in particular, I will give a detailed presentation about the latest progress we have made in the domain of wind energy. So the first part, I will give an overview of the work I've carried out during the ConFlex fellowship, and including all the 3 parts and also the corresponding publications. Then in the second part, I will talk about my work on the spatial temporal wind field predictions based on physics-informed deep learning and LiDAR measurements. And in this part, I will include the results for 2-dimensional wind field and 3-dimensional wind field predictions in front of the real-world wind turbines. So this is the illustration of the overall research I've carried out. So our research begins with the individual turbine level, focusing on the structure control of wind turbine structures by using tuned mass damper. And the purpose is for the load mitigation of individual wind turbines. And then our research moved to the farm level, considering the weak interactions between individual wind turbines for the control purpose and monitoring purpose. And the third part is the wind field prediction, which is very important for the performance improvement for both the first part and second part. For example, it can provide preview information for the control, and it can provide real-world wind field estimations for the modeling of wind farms. As the approach we've taken, because the underlying structural system and fluid system is very complex and strongly nonlinear. So, and on the other hand, the machine learning approach is very powerful in handling nonlinear systems. Therefore, we've designed and employed the latest development in machine learning community. So in particular, for the control purpose, we've designed reinforcement learning-based approach for the control of individual wind turbines. And for the wind farm part, we've designed a surrogate modeling approach based on both supervised and unsupervised learning approach. And as for the third part, we've designed physics-informed deep learning approach to combine data and physics in a unified framework to achieve wind prediction. The first part is the control of wind turbine structures. So this part, I have presented the main results in our UoW meeting. And this part, we've designed reinforcement learning method to do the control design of floating wind turbine and also monopile wind turbines. And this design approach can take account of the nonlinear dynamics of the structural system. Therefore, we can achieve good performance for both strong wave and wind condition and also normal wind and wave conditions. Then for the wind farm weak modeling part, we begin with the investigation of traditional weak models, focusing on the parameter uncertainty of analytical weak models. And after that, we move to the development of novel wind farm weak models by machine learning-based surrogate modeling approach. And for this part, we developed both the static weak models and also dynamic weak models. And another line of research in wind farm is that we also carried out the intelligent control design for wind farm power generation control, so to maximize the power generation of a wind farm. And for this part, I have collaborated with one of my colleagues at Warwick to use deep reinforcement learning and high fidelity simulations to achieve the optimal control design. And for the third part, which is the wind field prediction part, the motivation is that currently for large wind turbines, LiDAR is becoming available to measure the wind information in front of the wind turbines. However, it can only provide point measurement. So the wind field information cannot be measured directly, but it is very important for the load mitigation of individual wind turbines and also to model the real world wind farm wind field. Therefore, in this part, we developed deep learning approach to predict the 2-dimensional wind field at turbine hub height, and also the full 3-dimensional wind field experienced by the wind turbines in real world conditions. Therefore, it is very important for further development in wind energy. to summarize, so during my ConFlex fellowship, I have published 7 high-impact journal papers and 1 conference papers as first author, and I also co-authored 1 high-impact journal papers, and I have another journal paper currently under review. And also, I finished my PhD studies, submitted a thesis in this domain of machine learning-based modeling and control of wind turbine and wind farm systems. And currently, I'm continue working in this line of research at University of Warwick, and I plan to stay in academia, but I'm also very interested in seeking collaboration with industrial partners to generate real-world industrial values based on our progress. And because the first part and second part, I have presented them at the first billable meeting and at the virtual meeting last year. And today I will focus on the third part, which is spatial temporal wind field prediction based on LiDAR measurements and physics-informed deep learning. And for this part here, this is an illustration of the LiDAR measurement system in front of the wind turbines. Here, this is 2 LiDAR beam settings. So with a half angle of 15 degrees between the LiDAR beams. As we can see, the LiDAR can measure the line of sight on speed at discrete locations marked as cross signs in this figure. There are 2 important limitations for LiDAR. First, it can only measure the line of sight on speed, meaning that it can only measure the wind speed vector projected in the LiDAR beam direction. So it is scalar measurement. The wind direction is not measured in LiDAR. Second, it can only measure the wind speed signal at sparse spatial locations. So here, for example, it can only measure the wind speed signals at these in overall 12 points. So we want to know the whole picture in front of wind turbine. So this is not achievable by LiDAR directly. And on the other side, this is an example of the LiDAR measurement signal. Here, each line represents the line of sight wind speed measurement during the considered time period at one particular location. So clearly, if we want to know the whole picture in front of wind turbines, this cannot be achieved by using data alone. So in this part, we developed a deep learning model that can combine flow physics with LiDAR in a unified manner to achieve the prediction of the whole flow field in front of the wind turbine, including the location that no measurement is available at all. So this is the overall flow chart. So first, we construct a deep neural network that can map the spatial temporal coordinate t, x, y to the corresponding flow state at this spatial temporal coordinate. Here, the psi is a stream function and the p is the pressure. And based on this deep neural network, we can encode partial differential equations through physics-informed deep learning technique. So in particular, for example, here, we can use automatic differentiation to derive the derivative of psi with regard to the coordinate y, the input y. Then we can obtain the streamwise velocity u. So this can be done in a similar way for every terms in the Navier-Stokes equations, and eventually we can encode the Navier-Stokes residue terms in the deep neural network. So after constructing this part, the pink part is the physics-informed part. It actually takes the txy as input and returns the EU and EV, which is the residue terms of the momentum equation as the output. And similarly, we derive the deep neural network 2, which takes the txy as input and returns the line of sight wind speed measurement as the output. So here f is the observation function, which takes the wind speed vector and project it into the LiDAR beam direction to obtain the line of sight wind speed signal. And the training of this deep learning models aims to minimize the loss function, which is defined as a sum of L1, L2. L1 here is the loss function of the Navier-Stokes residue terms, and L2 is the loss from the LiDAR measurements. So the minimization of L1 will enforce the constraint imposed by Navier-Stokes equations, and the minimization of L2 will make sure that the neural network to fit the LiDAR measurement signal. And this is done simultaneously. Therefore, we combine the LiDAR measurement with Navier-Stokes constraint in a unified manner in the neural network training process. After training, we can directly feed any spatial temporal coordinate Tx, Y of our interest through this DNN2, and we can get the velocity in each direction here in X and Y direction through DNN2 at that location and at that time instant. And this X and Y include the locations that the measurement is carried out and also the locations that no measurement is available. And also the only data required is the scalar LiDAR measurements, and the neural network after training can predict the velocity vector field, including the component in X, Y, and Y direction. And in order to validate the approach we proposed, we carried out large eddy simulations at the high performance computing facility at Warwick to demonstrate how it performs. Here, this is the baseline case for a 2D case. In this case, the wind comes from the turbine yaw direction, which is the most common scenarios in wind industry. The top video shows the prediction results. The bottom video shows the corresponding ground truth, which is generated by large eddy simulations. And in this case, the only measurement data we require is the measurement, the line of sight measurement at the locations marked as cross signs. This is a 2 LiDAR beam sighting, and each LiDAR beam measures the wind speed signal at in total 11 measurement points. So in total, 22 locations are measured. And after training the deep learning model, we can predict the whole thing in front of the turbine at every time instant. We can see that our prediction match with the true value very well. And also the high speed zones, the low speed flow structures are all predicted very well. For example, this red dot, this is actually presenting a wind gust in the applications. It is captured to enter the flow domain, travel through it, and eventually hit the wind turbine structure at the right side. So this kind of performance is very important and useful in evaluating and control the wind turbines to reduce their loading. And based on the wind field predictions, we can extract important information for wind applications. First, we examine the performance in predicting effective wind speed, which is defined as the wind speed at a particular streamwise location X averaged over the Y direction, the spanwise direction. And here, this is the results for 4 different streamwise locations. And here, the true value is shown in black and the prediction value shown in red. We can see that we accurately predict the change of the wind speed along time very well for all the locations. And also we can we can extract the instantaneous wind speed at turbine blade locations to see how the performance of the proposed method in predicting the wind speed experienced by the wind turbine. Here, this is the results at corresponding to the turbine blade root, half chord length, and turbine blade tip. And we can see that we achieved a fairly good accuracy. And in addition, we can, because the Navier-Stokes equations is incorporated in the deep learning model, and it contains the dynamic term, the partial derivative with respect to time coordinate. Therefore, the deep learning model also learns the dynamic behaviors of the wind field. Therefore, we can directly feed future time instants into the deep learning model to carry out short-term wind forecasting. So in these figures, I also included the 15 seconds ahead wind forecasting for the turbine, for the wind speed at turbine locations. As we can see, a fairly good accuracy is achieved. And this is very important because our prediction does not rely on the frozen turbulence hypothesis, which is commonly used in previous studies. And in order to fully validate the approach, we've considered a set of different cases with various level of measurement noise, different spatial resolution, temporal resolution, LiDAR look direction, and also free stream different free stream turbulence level. And for all these conditions, we calculate the prediction results for the wind speed magnitude and the wind direction. And the root mean square error here shows a consistent accuracy for all the cases we considered, demonstrating its potential in real-world conditions. And in order to further improve the approach, we extend it to three-dimensional cases because actual wind turbines live in three-dimensional, not in two-dimensional. And this is the results for the three-dimensional cases. The left video shows the prediction results and the right video shows the ground truth. And we visualize this three-dimensional flow field in the horizontal plane at half height and also the vertical plane. And we can see that the flow structures are all predicted very well. And also in 3D cases, we can also visualize the effect of atmospheric boundary layers. So the wind shear is clearly captured. So we can observe that the wind speed actually increases with altitude. And similarly, we can extract the effective wind speed to examine the performance. In this case, we define the effective wind speed as the wind speed averaged over the y direction instead averaged over the entire rotor plane. Because in this way, we can clearly show the change of the wind speed at different height. And this is the results for 5 different streamwise locations. And for each location, we give the results for 5 different time instants covering over the considered time period. And the black line shows the true value and the prediction value are shown in red line. We can see that they match with each other very well, and also the wind profile in the vertical direction is clearly captured. And in this case, it's more interesting to see the instantaneous wind speed at turbine blade locations, because this is 3D wind field, and we can according to the rotation speed of the turbine blade, we can track the wind speed experienced by the wind turbines. Now here, this is the wind speed signal at 5 different turbine blade locations, ranging from blade root to the blade tip. We can see clearly that the effect of wind shear, the oscillation, so the change of the wind speed increases from turbine blade root to turbine blade tip, because the turbine blade tip location, it travels in the atmospheric boundary layers from lower altitude to higher altitude. So it experiences this change of wind speed dramatically than the blade root location. And our approach successfully captured all the mean change of the wind speed. This is very useful for the wind turbine control. And also, we carried out a set of test cases to show the performance of the method. And these cases range from the 8 meter per second incoming wind to 23 meter per second wind speed. And this covers the below rated and above rated operation conditions of typical wind turbines. And also, we give the results for both for the wind speed vectors component in X, Y, Z direction. So here U, V, and W. And based on these wind speed components, we can also calculate the wind direction. So here the gamma Y is the horizontal wind direction, which is a conventional wind direction we speak about. And here the gamma Z is the wind direction in the vertical plane. So this is usually ignored in measuring the incoming wind speed, because this is not, in most cases, it is not available. But with our approach, we can estimate this gamma Z, which is also very useful for example, control and design the turbine tilt angle, because turbine actually is not directly in the vertical plane. Actually, it have a tilt angle. And we calculate the root mean square error of our approach for all the cases. As we can see here, the prediction error remain consistently small. So to summarize, we have, in this part, we developed a deep learning model which can combine limited sparse data, which is the LiDAR measurement data, with physics. Here in this case is either 2-dimensional Navier-Stokes equation or 3-dimensional Navier-Stokes equation. And we combine the LiDAR and physics without model reduction. And for the first time in the literature, we achieved the prediction of the three-dimensional wind field in front of the wind turbines. In addition, short-term wind forecasting is achieved without using Taylor's frozen turbulence hypothesis. And in the future, the predicted wind field is very useful to the other wind energy research, including wind resource assessment, wind turbine control and monitoring, and also the load and power forecasting of wind turbine structures. That's all for this part. Thank you for your attention. Any questions?